Okay, pickled peppers. So, during our last discussion, we started talking about these different forms of separation that can take place in the chromatography column. And we listed 5 different ones, and we related those to the actual instrument. So, adsorption, partition, ion exchange, molecular exclusion, and affinity. So what we need to do is we need to go in now and talk about each one of these in detail. How are they different from one another? What makes adsorption different than absorption or the other separation techniques that we might see? And that's the very first one that we're going to talk about now. So the term that we're going to use is adsorption with an AD, not an AB. I don't have abs, and adsorption doesn't have abs either. So adsorption is what takes place in chromatography. There's a slight difference between adsorption and absorption. Okay, so what's the difference? Well, if something absorbs something, what does that mean, right? So absorbs basically means engulfs in a way. So imagine this big flat blob that's here and a tiny little molecule out here to the side. So if absorption takes place, what happens is that that little molecule will kind of get near the big fat blob and in it goes. All right. And you don't really want that to happen in chromatography, because if adsorption takes place, then it's very difficult for this molecule to leave that blob that we're going to call the stationary phase. Okay. So we never really want to see this happen. If it goes inside of the stationary phase, it's never going to get released and it's going to stay there forever. And that's not really how chromatography works. So adsorption is not what we want to see. Okay? What actually happens in adsorption is that the molecule will kind of come near the stationary phase and it just kind of hangs out on the surface and it stays there for a little bit. I normally talk about this fly paper. If you've ever went to someone's house, especially if, you know, they were your grandparents or maybe a little bit older, instead of fly swatters, what they would use would be fly paper. And it would be this paper with this sticky glue on it. And these flies would get near this sticky paper and their feet would get trapped onto the glue and they would just kind of hang out there. And eventually they would just take it and trash it. But imagine this molecule being covered in that sticky fly paper. So that's really what stationary phase is. It's this molecule that we'll get into in just a second. And on the outside surface, we have this sticky fly paper that happens, right? And the molecule will come in and it will stick to the surface temporarily. And then it just kind of leaves and it goes on to the next stationary phase particle. And that's kind of adsorption at its best, right? So in the field of HPLC, UHPLC, LC, most of the time adsorption is taking place in those types of instruments or pieces of equipment. TLC is also absorption, and there's other methods of chromatography out there too that play off of absorption, just like packing your own column would do, right? So that's adsorption. So you're going to get a test question. You know that it's coming your way, and it's going to say, explain the difference between adsorption and absorption. And know that adsorption is what takes place in chromatography, and that basically means that these particles basically stick to the surface of the particle, the stationary phase in this case, and then they hang out for a little bit, and then finally they dislodge themselves and they move on to another fat blob that we're going to call a stationary phase particle. Okay, that's all there is to adsorption, nothing fancier than that. So this is a diagram that comes from the chemical analysis textbook that basically kind of describes adsorption the best way that it can. So here we see this big fat blob, and these blobs have fingers. That's basically the stationary phase particle. You know, it's just this massive kind of emulsion type of material that's inside of the column, and there's just fingers and pricks all over the place, and all of these black dots are basically your particle that you're trying to separate. So these are the components inside of your mixture that you want to separate from each other. So what they're basically showing is that these little black dots are just sticking to the surface. That's all that they're doing, and then they're going to get dislodged, and they're going to be kicked off again to another part of the stationary phase. But that's why it says the solute is adsorbed on the surface of the stationary phase. And that's what we call adsorption chromatography. So it's a solid stationary phase and a liquid or gas mobile phase that can be used in the setup. The key here, though, is that it's a solid stationary phase. Solute is adsorbed on the surface of the particles, and the more strongly a solute is adsorbed, the slower it travels through the column, right? So the longer that they hang out with the stationary phase, it's going to take them longer to move through the column and out the other end to get detected. And that kind of hopefully makes a little bit of common sense, right? So we'll talk about the attractions and that kind of stuff a little bit later on, but this at the heart is what we call adsorption chromatography. Now, the next one that we're going to focus on is something called partition chromatography. All right. So if you look at the partition chromatography, it looks very similar. I see this big fat blobby-like substance that they've drawn in the diagram, right? And then if you take a look at the surface, it's basically all of these molecules that you want to separate from each other, and they're hanging out on the surface as well. But if you've noticed, these particles are kind of covered in a hazy like in the diagram, right? It's a hazy area that you're seeing they're kind of stuck to. That hazy area represents something. So how is partition chromatography different than adsorption chromatography? Well, if you take a look at this diagram from the textbook, it's going to say that the solute dissolved in liquid phase coated on the surface of a solid support. All right, so let's read that again. The solute, which is what you're trying to separate from each other, dissolves in a liquid phase that is coated on the surface of a solid support. So that basically means that this is the stationary phase particle here, and that stationary phase particle on its surface has this jelly-like material that's all over the surface of it. And that jelly-like material is what captures the molecules as they go through. Now, if you take a look at adsorption, you don't really see that jelly-like substance, right? This is just the full-blown stationary phase particle. That's what we're using. In partition chromatography, it's a little different because we get this really thin layer of this jelly-like stuff that's on the outside surface of the stationary phase. And it's that jelly-like material that really holds these compounds back. So here at partition chromatography, a liquid stationary phase is bonded to a solid surface, and this says it's typically inside of a glass column. And the solid equilibrates between the liquid stationary phase and the mobile phase, which is typically a gas. So if you go back to this kind of note slide that we did, and I've already erased it, but we are going to see partition chromatography take place in the world of gas chromatography. That's really where we find partition chromatography finding its home. So liquid phase on the stationary phase. And it's this liquid that kind of traps these components as they come through. Those components are typically a gas, and they hang out in this liquid jelly-like layer that's on the surface of the stationary phase. And that's why this says a glass column, because gas chromatography uses glass columns more than they use actually stainless steel columns or metal ones. So that's why you're seeing this notation of a glass being inserted here, and that's why you're seeing that the mobile phase is normally a gas that will go through and force this separation to take place. So that's the story with partition. Very similar to adsorption. The difference is that this has a jelly-like layer on the outside surface that will hold your molecules behind and retain them a little bit. All right, so your next one is ion exchange chromatography. And the ion exchange chromatography works on a completely different principle. We still see a stationary phase, right? And this stationary phase is still going to kind of promote the separation from taking place, but it operates a little differently. So with the ion exchange, what we see is a stationary phase particle, and I'm just going to write it as a blob again. And that stationary phase particle on its surface has various groups. And these groups can either be positively charged or these groups can be negatively charged, right? That's really up to the analyst to decide, and that's really what you're trying to analyze. That's why you've got two different choices. It's either going to be positive or it's going to be negative. It's like a magnet, right? Okay, so if these things are positive groups, it's typically an ammonium complex. So I'm going to do an NH4 for now. And keep in mind that this has some alternate forms. And down here at the bottom, I'm just going to put alternative forms can exist. So it can be a nitrogen with 4 hydrogens, a nitrogen with 1 hydrogen and 3 alkyl groups, a nitrogen with 2 hydrogens and 2 alkyl groups, a nitrogen with 3 hydrogens and 1 alkyl group. Basically, there's all kinds of different choices that are out there, but the NH4 is going to be the most simplistic by nature, and plus, it's the easiest to write. So why not choose that one? So that's NH4 or ammonium. The stationary phase can also have a negative charge species on it, and this is going to be SO3. And that SO3 group is basically a kind of the tail end. If you're looking at the penny, heads and a tail, well, cup half full, cup half empty. Well, this is two sides of the same story. One's going to be the positive side, one's going to be the negative side. So the SO3 group is actually going to be a piece that can attract certain components in your mixture and help separate those components in the mixture from each other. Now, we'll get into more detail about how this happens when we get into the world of ion exchange and ion chromatography, but for now, I think that this does a pretty good job basically telling you how they're different. So this one's a full-blown charge that attracts the opposite charge to it, so it can help separate your components from each other. So that's ion exchange, and more about that later. If you want to see a diagram for now of ion exchange, this is typically how your textbook will note it. So we see a stationary phase here, and that stationary phase particle has either positive or negative pieces on it. So what happens is that the sample goes up here to the top, and then over time, the components will begin to separate from each other, and that's what you're seeing here. And then finally, the opposite charges will tend to come off with just your mobile phase going through it. It's enough strength to kind of push it on out of the column itself as you need it. All right. So I'm going to stop here, and in the next video we'll pick up with molecular exclusion and the affinity, and we'll talk about how these are different as far as how theoretical wise the separation begins to take place. So come back and see me, or come back and listen to me, and take some more notes on the molecular exclusion and the affinity chromatography in the next video.